Hello, welcome. Today's video is going to be about basic chemistry. And so, although this is not a chemistry class, there is a lot of chemistry involved in biology, and it is very important that you know the basics. So I am just going to wrap this up into one video and just let you know what you need to know for the biology stuff. And when you mix biology and chemistry together, that's called biochemistry. And so that's going to be the title of our notes today. Biochemistry. Okay, so I'm first going to start off by saying that everything in the whole wide world and the whole universe is made of stuff. And that stuff is, if you go down to the smallest part of all the stuff, they are called atoms. So everything is made of atoms in the whole universe. And there are only a certain number of atoms, okay? And so these are the building blocks for everything in the whole wide universe. And there are some properties that atoms have, okay? And so a lot of this should be familiar to you, but I'm going to pull in a periodic table, and a periodic table shows you all the possible atoms. Okay, so here is the periodic table. A lot of times in a classroom, you'll see one of these displayed on the wall. And so in this periodic table, you can see that there are about 118 different atoms types, and those atom types are called elements. Okay, elements are a type of atom. Okay, and in this periodic table, you can see that there are about 118. So this is the biggest one. And so we put them in a periodic table just to have them organized. It's easier for us humans to be able to put them in this way so that we can see which atoms are similar to other atoms and put them in an organized way that have similar patterns. But so in terms of biology, every single living organism has 6 of these atoms no matter what. Okay, so in all living things, 6 atoms are present. Okay, and you need to memorize these. Those are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Okay, and so those are the 6 atoms that are found in all living organisms. And of course, living organisms have more than just these 6, but all living organisms have these 6 no matter what. And so I'm going to circle them on the periodic table so you can see where they are. So here's carbon, and then hydrogen is over here is number 1. Here's nitrogen, here's oxygen, phosphorus, and sulfur. Okay? And so those are the 6 that are found in all living things. And I want to point out that there is this line here where you can see there's these purple elements. Everything to the right side of that, those purple ones are called nonmetals, and everything to the left of them are metals. So all of these are nonmetals. So living organisms are made of nonmetal elements. Okay, so the way I remember these 6 elements is I just remember this word chinops, and that's how I remember it. And so we're going to talk about these different atoms, okay? And basically, they are the building blocks of all living things. Okay, so first let's talk about what an atom is. Um, Atoms are very teeny, teeny, tiny, and we cannot really see an atom with a microscope because it's too small. But there have been some technology that has been developed where you can see like what an atom would look like based on some pattern it reflects when you throw electrons at it. But we use what's called a Bohr model to represent a model of an atom. Okay, so we use what is called a Bohr model. This is not super exactly accurate, but it's very helpful in trying to understand what an atom has and what it looks like. So it's called a Bohr model, and that's what we're going to be using in this class. And the way that we write a Bohr model is in all atoms, atoms have a nucleus, which is the center, and then it has this outside part, okay, which are called shells. So there's a nucleus center, a nuclear center, and then these shells on the outside of that. So when you draw a Bohr model, what you do is you put what's in the nucleus first, okay? And before I do that, I'm going to pull in carbon so you can see what I'm talking about. So here's a carbon from the periodic table. I'm just going to blow it up so you can see it up close. Okay, so that's a little bit too blown up, but here is carbon from the periodic table, okay? And before I draw the Bohr model, I need to point out a couple of things. When you read the periodic table, hang on here, let me shrink that back up. Each square in the periodic table has some information in it. So let me introduce you to that information. In each of these, we have the name of the element, okay? And so that's not on every single periodic table, but on some they have the name, okay? Then there's a number on the top of the square, and this is called the atomic number, okay? And I'm going to tell you what that atomic number stands for in a second. Then we've got one or two letters, and this is called the atomic symbol. Okay, for carbon, it is C. Sometimes the name of the element doesn't match up with the letters. For example, let's look over here. Let me look at a good one. Let's see right here. Fe stands for iron. And there are reasons for this, and you could Google that and find out what it is. But like gold is Au. So sometimes the letters don't match up exactly to the English word. But for carbon, it's C. And then down here we have another number, which is usually not a whole number. So it's going to have a decimal, and this is called the atomic weight or atomic mass. Okay, so that is information that's given to you in the periodic table if you look at each individual element. Okay, so what I want to point out before I draw the Bohr model is that this atomic number tells you how many subatomic particles you have in an atom, okay? So let me first tell you that there are 3 different subatomic particles. So let me make a list here. Subatomic particles. There are 3. The first one is called a proton. And so subatomic particles means the parts of the atom. There are 3 parts of an atom. There are actually more than just these 3, but we're just going to go into the 3. So the first one is called a proton. Okay, and this atomic number here for carbon is 6. So carbon has 6 protons. Okay, and a proton has a positive charge. That's what you need to know about the protons. I'm just going to put a plus here. It has a positive charge. Okay, that is one of the subatomic particles. The other one is called a neutron. You have probably heard of this before. And the atomic number tells you the number of neutrons. So for carbon, carbon has 6 neutrons. And then the third subatomic particle is the electron. And an electron has a negative charge. The neutron has no charge. It's neutral, which is why it's called a neutron. Electron has a negative charge. And so carbon has 6 protons, 6 neutrons, 6 electrons. That's what the atomic number is telling you. Okay, so in a stable atom, it's going to have 6 of each. Okay, if you were to look at another one like nitrogen, which is number 7. So if you look at the periodic table, let's scoot up here. Nitrogen is right next to it. This is number 7. It has 7 protons, 7 neutrons, 7 electrons. Oxygen is the number 8. Has 8 protons, 8 neutrons, 8 electrons, and so on. Okay? Hydrogen over here is number 1. So it only has 1 proton, 1 neutron, 1 electron. Okay, so let me draw a Bohr model for you for carbon. Okay, and this is how we are going to represent atoms in this class. So you first draw the nucleus, and inside the nucleus, you have the protons and the neutrons, okay? So I'm going to write protons and neutrons are in the nucleus, and the electrons are in the outer shells. Whoops, sorry, outer shells. Okay, let me scoot that back. And so let's draw one. So we're going to put the protons and neutrons in the nucleus. And so the protons, there's 6 of them, and protons are positive. So I'm just going to write a 6, and I'm going to put a P for protons, and I'm going to put a little plus there, meaning that it's positively charged. Okay? Hang on, let me just fix that. It looks kind of weird. Okay, so I'm drawing the nucleus. I'm drawing a Bohr model of carbon right now. Also in the nucleus are the neutrons. So I'm going to put a 6 and I'm going to put an N. So what that means is we have 6 little protons buzzing around, 6 little neutrons buzzing around. Neutrons don't have a charge, so I'm not going to put a plus or a minus on it. And in the nucleus, there are 6 of these protons, 6 of these neutrons, and so together they make 12. The nucleus is what that gives the weight to the atom. Okay, the protons and neutrons have the weight. Electrons don't have any weight. They barely weigh anything. So this atomic mass right here, I'm going to circle it, says 12.011. This is coming from the protons and the neutrons in the nucleus of an atom. This number here is not a whole number, so it's not exactly 12, and it is representing the average weight of all the carbon atoms in the world. Okay, and I'll tell you why it's not a whole number in a second. But for our Bohr model, we have the nucleus, which is 6 protons, 6 neutrons. So I'm going to draw a shell outside of the nucleus. Okay, there's my first shell. And atoms can have up to 7 shells. Okay, let me just make sure of that. Hang on. Okay, so we have 1, 2, 3, 4, 5, 6, 7. Yeah. So atoms can have up to 7 shells, and in the first shell of every atom, it can hold up to 2 electrons. So for our carbon Bohr model, we have 6 electrons, okay, because we have 6 protons, 6 neutrons. I'm going to represent electrons with just a little dot like this. Hang on, let's see. Let me do that better. Oops. I'm going to draw it like this. I'm going to draw a little dot, color it in. That's 1 electron, and then here's a second electron. Okay, so I'm going to end up drawing 6 total electrons. The first shell can hold up to only 2 electrons. And this is for all atoms. All atoms can only hold 2 electrons in its first shell. Once the first shell is full, so it has 2 electrons, then you start doing a new shell, a second shell. So I'm going to draw a second shell here. Okay, and the second shell can hold up to 8 electrons. We are doing a total of 6 electrons. We have 2 electrons in the first shell, so we're going to draw 4 electrons in the second shell. Okay, because it can hold up to 8, but we only have 6 total. So now this is a Bohr model of carbon, which shows you that you have 6 protons in the nucleus, 6 neutrons in the nucleus, and you have 2 shells. 2 of the electrons are floating around in the first shell, and 4 electrons are floating around in the outer shell. Okay, so let me write some things down here. I'm going to say the first shell can only hold 2 electrons. Two, and I'm going to put an E with a little negative. That's how I write electrons. Okay, and then I'm going to put second to 7th shell holds up to 8 electrons. Okay, so you can fill them up to 8. Once the 8 is full, then you make a new shell. Okay, so I want to point something out in the periodic table. When you look at the periodic table here, this first row only has 2 elements, hydrogen, helium. So hydrogen only has 1 shell with 1 electron. Helium has 1 shell with 2 electrons. Then you jump to the next shell. This is the second shell. Lithium has only 1 electron in the second shell. Beryllium has 2 electrons in the second shell. Boron has 3 electrons in the second shell. Carbon, which we just drew, has 4 electrons in the second shell. We just saw that, and so on. Here's the third shell, fourth, fifth, sixth, seventh shell, okay? And so all atoms like their outer shell to be full, okay? That's when they're the most stable. This atom right here, carbon, is not stable like this, and you would never see carbon in the environment like this because it's unstable, okay? So what it wants to do is it wants to fill in this outer shell with more electrons. And the way that it's going to do that is it's going to join up with other atoms, okay? And we're going to talk about that in a minute. Okay, so before we talk about that, I just want to say that we've got protons, neutrons, and electrons in a stable atom. This number represents that, but some of these numbers can change, okay? So first I'm going to say that protons can never change number, okay? So I'm going to write this down. I'm going to scoot up here. We're going to write this down. The proton number, I'm going to write 1, 2, and 3. So the first point is the proton number can never change. Okay, so what I mean by that is, let's say we're talking about carbon has 6 protons. You cannot add a new proton. If you add a new proton into this nucleus, then you will have 7 protons, and now you have nitrogen. Okay, that's how you make new atoms. You add a proton, and we do that. If you look at the periodic table, most of these elements are not found naturally in the world. They were made in the lab. And like, for example, these big atoms down here on the bottom, they only exist for a split second in the lab. And that's because a scientist is adding a proton to the nucleus just to see if it exists. And so no one has been able to lately to make the 119, but I'm sure somebody will one day. And then, add another one to 120. But these don't exist naturally. Okay, they're too unstable. Okay, so what I want to say is the first point is the proton number can never change. If you change the proton number, you are now talking about a different atom. Okay. Rule number 2 is the neutron number can change. Well, I'm going to say when the neutron number changes, what we have now is called an isotope. So when the neutron number changes, it becomes an isotope. Okay, an isotope, that is a vocabulary word. I'm going to highlight this. Okay, isotope. Okay, and so the neutron number can either be bigger or smaller than what the atomic number is. Okay, so for example, we are looking at carbon here in this Bohr model. It's only allowed 6 protons, okay? Like I said, if you add a new proton, you now are talking about nitrogen. So we're not changing the proton number, but we can change this neutron number. If we change this neutron number and add it and make it 7, hang on a second, I want this. I'm going to cross that off, and let's say we add a neutron, okay? Now it's got 7 neutrons, and now it's a little bit heavier. Okay, it was 12 was the weight. Now it's 13. And now we have what is called an isotope. Okay, so I'm going to say, for an example, is a normal carbon. I'm going to write normal carbon is carbon 12 is what it's called. And this is how it's written, which means the weight is 12, which means it's got 6 protons, 6 neutrons. An isotope of carbon is called carbon 13. Okay, and that is 1 extra neutron in there. It's a little bit heavier, and so isotopes are radioactive. And what that means is that they are a little bit unstable. Okay, so they're not very comfortable having this extra weight on their nucleus. So what'll happen is they'll break apart. Okay, the nucleus will break apart. Something like carbon 13 doesn't cause doesn't release a lot of energy when it breaks apart, but there are some radioactive isotopes that cause a huge explosion, like uranium, for example. When uranium falls apart, it causes an atomic bomb. That's what an atomic bomb is, okay, when an isotope falls apart. And all isotopes fall apart because they are unstable. Carbon-13 is not a big deal. There's a lot of carbon-13 in the world, and it falls apart all the time. And we actually use it to measure things like rocks. That's how we measure our fossils, to see how old our fossils are. We measure how much carbon-13 has fallen apart because it falls apart at a certain rate. Okay, anyway. So we cannot change the proton number. Number two is we can change the neutron number, and that gives us an isotope. And then the last point is that if you change the electron number, what you make is an ion. So when the electron number changes, it becomes an ion. Okay, and let me explain. So we've got this carbon here, and we have electrons. Okay, so let me explain about the electrons. The nucleus is a very solid mass that has weight. Electrons are these tiny little particles that move around and they buzz around real fast, always moving, and they just move around the nucleus. When I drew this sphere here, it's a three-dimensional sphere. And the two electrons in the first sphere are just buzzing around in a three-dimensional way, and it never stops. Okay, it's just always moving, but it's away from the nucleus. And then there's another shell around, that's another sphere around the first shell, and the electrons are buzzing around that shell. Okay, and they are always moving, and they are far away from the nucleus. So there is a lot of space in between the nucleus and the first shell, and there's a lot of space between the outer shells and the inner shells. Okay, so there's a lot of air in there. And so in a way, all matter, so all stuff, has a lot of space in it because atoms have a lot of space. Okay, but electrons very easily come off and come on. Okay, and so we said that electrons have a negative charge. So if you add electrons to an atom, it becomes a negative ion. Okay, so I'm going to write this down. A negative ion has extra electrons. And this has a special name, and it is called an anion. Let me write that down. Negative ion has extra electrons, and this is called an anion. Okay, that's a vocabulary word. Let's highlight that. And so that's because you're adding negative things. Okay, electrons are negative things, so it's going to make it more negative. A positive ion has less electrons. It loses electrons. Positive ion lost electrons. It could be one, but it could be more than one too. Lost electrons. And this is called a cation. Okay, I always remember cations because cats are cute and cats are a good thing, and cats are a positive thing. So I always remember a cation means a positive ion, and the other one, which is an anion, is a negative ion. Okay, and so an atom can gain electrons or it can lose electrons. If it gains electrons, it's a negative ion, which is an anion. If it loses electrons, then it's a positive ion. Okay, and then it'll have a positive overall charge. The weight does not change when you have an ion because, like I said, electrons have no weight. Okay, so the last thing that I want to talk about before I end the video is this idea of chemical bonding. Okay? Okay, so chemical bonding. Okay, so atoms can interact with each other, and they do all the time. Okay, like I said earlier, you never actually see an atom all by itself. They are always interacting with other atoms. And so when two atoms interact with each other, this is called a chemical bond. And I'm going to explain three different chemical bonds. Okay, I'm going to explain the strongest bond first, then the medium one, then the weakest bond last. Okay, there are more than just these bonds. These are just the bonds that are important for our class. So this first bond is called a covalent bond. And like I said, this is the strongest bond. It's a strong bond. And it is a relationship between two atoms, and it is a strong relationship between two atoms. It's kind of like your friendship with your super best friend from your whole life. Very strong. And what a covalent bond is when you have two atoms that share electrons. Okay, I'm going to write that down. This is when two atoms share electrons. Let me explain with an example. I'm going to use water as an example. So as you know from kindergarten, water is made of H2O. Okay, so this is going to be my example. Let me change colors here. I think I'm going to go with brown. Okay, water is H2O. What this here means is that we have two hydrogens and one oxygen. And so I'm going to draw a Bohr model of water so we can see what it looks like. So if you look at the periodic table, oxygen is, let's see, 6, 7, 8 in the periodic table. Okay, so I'm just going to scoot up here so you can see it. Okay, right here. So here's 5, 6, 7, 8. So the atomic number is 8. What that means is that it's going to have 8 protons in the nucleus. So I'm going to draw a water molecule using a Bohr model. And so the oxygen is going to go here. We have 8 protons in the nucleus. Protons are positively charged. And then we have 8 neutrons in the nucleus. Then we have 8 electrons. So I'm going to draw my first shell here. And we're going to put 1 electron here, the second electron here. The first shell can only hold 2 electrons. So then I'm going to draw another shell. And I'm going to put 1 electron here, another electron here, another electron here, another electron here. And so we need 8 total. So this is only 6. So I'm going to put a 7th one here and an 8th one here. Okay, and electrons outside of the first shell, they like to be paired up. Okay, so they like to stick together in pairs. And it also helps us in a Bohr model to see where the missing electrons are. And so like I mentioned, atoms like to have their outer shell all the way full. So, and that is the most stable configuration for an atom. And so this atom has 2 missing electrons until it has a full outer shell to have the full 8 on the outside. So it's going to join up with 2 other atoms, and those 2 other atoms are going to be hydrogen. Okay, and we know that water has 2 hydrogens. So I think I'm going to make these blue so we can distinguish between the hydrogen and the oxygen. So this brown atom is oxygen, and now I'm going to draw the hydrogen. So there's 1 proton in the nucleus of a hydrogen, 1 neutron. Okay, and then I'm going to draw the shell. This is the first shell, and it only has 1 electron, and it's going to share its 1 electron with oxygen. And oxygen is going to share its 1 electron with hydrogen. So now hydrogen has a full outer shell. It's very happy because it only has 1 shell and it only needs 2 to be filled. And now the outer shell of oxygen is almost full, but it needs one more atom to share with. And so it's going to grab another hydrogen. So here's another hydrogen. It has 1 proton in the nucleus, 1 neutron in the nucleus, and 1 electron that's going to share with. And so this is what a water molecule looks like. And it always has this shape, okay? In my mind, it looks like a Mickey Mouse head. And so water always has the Mickey Mouse ears like this in that exact shape. This is what water looks like at the molecular level. And it's so stable. And it's very, very important for life. And so this is what a Bohr model looks like for water. And what I want to point out is that this sharing of electrons here is called a covalent bond. This right here that I'm circling is a covalent bond. Okay, covalent bond, and it's very, very strong. And water is very, very stable and very important for life. Okay, so that's one bond. The second bond is called an ionic bond. Okay, it is less stable, easier to like pull apart compared to the covalent bond. And I'm going to write it here. Number 2 is called an ionic bond. Okay, it is like medium strength. Okay, hold on. Let me just make sure I'm consistent. So it's a capital B. And an ionic bond is when one atom donates electrons to another atom. Okay, instead of sharing them together like we saw with the water molecule, one atom is just going to give up its electron and give it to another atom. So I'm going to say when one atom gives up an electron, it could be more than one, gives up an electron to another atom. Okay, let me show you through an example again. Okay, this example is going to be sodium chloride. Okay, so I'm going to put, this example is called sodium. Sodium is Na, chloride is Cl. And if you didn't know this already, sodium chloride is salt, table salt. So this is the salt that you eat every day, like on your French fries. And it's very stable, obviously, because we eat it and you can still taste it, even though you're crunching it. And so table salt is made of a sodium and a chloride that are stuck together. Okay, so let me draw the Bohr model so you can see what I'm talking about. Okay, so sodium, Na, we got to look at the numbers. Let me just pull up here. The periodic table. Sodium is right here, is 11, and chlorine is right here, it's 17. So sodium is 11 and chlorine is 17. Let me just write that down. 11 and 17. Okay. Okay, so I'm going to draw a Bohr model so you can see what's happening exactly. So a sodium atom has 11. So I'm going to draw the sodium in brown. So it has 11 protons, 11 neutrons, and then in its first shell, it's going to have 2 electrons. And then in its second shell, it's going to have 8 electrons. So I'm going to put 1, 2, 3, 4, 5, 6, 7, 8. And then that's 10 so far. So now we need to move to a third shell. Okay. And this one is only going to have 1 electron all by itself, lonely and very unhappy. So like I said, the atoms like the outer shell to be all the way full. And this one is barely full. So it does not like that. Okay. And so I'm just going to write right here that this is sodium. I'm going to put an arrow. Okay. So let me draw chlorine. Okay. I'm going to draw that in blue. Chlorine is number 17. So it has 17 protons in the nucleus, 17 neutrons in the nucleus. And then I'm going to draw its first shell. Whoops. And so the first shell always has up to 2 electrons. I'm going to draw a second shell. And this is going to have 8 electrons, which is going to bring it up to 10. And then it's going to have a third shell. And the third shell is going to have 7 electrons. Okay, so here's a Bohr model for chlorine. So this is chlorine. I'm going to put an arrow. And it's got 7 electrons in its outer shell, but it wants 8. And sodium has only 1 electron in its outer shell, but it wants 8. So what's going to happen when these two atoms get close together is this electron is going to hop off of sodium and jump onto chlorine. And it's going to come over here. So I'm going to draw this brown electron and put it here. And then what's going to happen is this electron disappears. And so now it doesn't have that shell anymore. So it loses the whole shell. And now this second shell is full with 8 electrons. So now sodium is stable with an outer shell with 8, and chlorine is stable with an outer shell of 8. And so now what has happened is sodium lost an electron, which makes it positive. So sodium is now a positive ion, which is a cation, and chlorine is now a negative ion because it gained an electron. And so it is it's an anion. So sodium is a cation, chlorine is an anion. And because one is positive, one is negative, and opposites attract, there is going to be an attraction between these two atoms so strong that they're just going to stick together because one's positive, one's negative. They're going to stick together forever and become your salt that you eat on your French fries. That bond between the two is called the ionic bond. So I'm going to write that here. Ionic bond is the attraction of opposite charges from losing and gaining electrons. So I'm going to write that down. Ionic bond is the attraction of opposite charges created from gaining and losing electrons. Okay, so that is the definition of an ionic bond. Okay, ionic bond here. Okay, the last bond is the weakest bond of all of these, but it comes in handy to have weak bonds sometimes. So I'm scooting up, and I'm going to put brown. This is number 3, the last bond and the weakest bond of all. This is called a hydrogen bond. Okay, and I'm just going to write this is the weakest bond. And like I said, what I was about to say is that it's handy to have weak bonds sometimes, because sometimes you just want to hold two things together just for a short time, like a temporary hold. And you want to be able to take them apart easily. Okay, so this is handy in biology. Okay, and so hydrogen bond, what this is when it's kind of like an ionic bond where two molecules are attracted to each other because of opposite charges, and one of the atoms has to be a hydrogen. That's the definition of a hydrogen bond. So let me write that down. When two molecules are attracted to each other because of opposite charges, and one of the molecules has a hydrogen. One of the molecules has a hydrogen. That's an official definition of a hydrogen bond. Okay, let me show you through an example. Oh, did I mess up on the colors? I think I did. I think I'm gonna go with blue for my example. Oops. Sorry. This board's a little touchy. Okay. Let's see. Let me just go with green. Okay, here's my example. So we talked about water earlier, and we talked about how within the water molecule there are covalent bonds. And so I'm going to draw a water molecule here. Let me do a better circle. So here's one water molecule. Okay, here's another water. That's one water molecule. Here's another one. Actually, I'm going to put it here. Okay, I'm going to scoot up a little bit. I'm going to draw a third water molecule. Okay, so I have three water molecules here. And so when you have like a cup of water, what it is millions of water molecules. Here are just three. And so I want to point out that when we look at this water molecule up here that I drew earlier in detail as a Bohr model, I want you to notice that all these electrons are mostly stuck on the oxygen. Okay, the the electrons are not really in the shell of the hydrogen. They're stuck to the oxygen over here. So in a way, the oxygen is hogging all the negative electrons, and the hydrogens don't have a lot of electrons buzzing around. And so what ends up happening is the oxygen part of the molecule is more negative charged, and the hydrogen part of the molecule is more positively charged. Okay, and so sometimes we write it like this. Like here is the water molecule. We're going to say the hydrogen, which is the Mickey Mouse ears, are more positive, and the oxygen, which is the Mickey Mouse head, is more negative. And it's partially more negative. It's not totally more negative. And so when you do a partial, we draw it like this. It's like a little delta sign. So it's like partially more positive up here, partially more negative down here. Okay, and so what's happening is now this molecule is not evenly charged all the way around. It's got kind of a positive side and a negative side. So now there's a difference in charge within the molecule. Okay, when a molecule has a difference in charge, this is called a polar molecule. Okay, I'm going to write this down for you. This is a concept that shows up in biology a lot and in science in general. Polar means that one side is different than the other side. That's all polar means. I'm going to write this down. One side is different than the other side. Okay, and this doesn't have to be about charges. It does refer to charges in what we're talking about right now, but it doesn't have to be that. For example, my body, my head looks very different than my feet. They're totally different. So I am a polar being. A tree, the leaves on the top are very different than the roots underground. A tree is polar, okay? A beach ball is the same all the way around, so it is non-polar, okay? You get that concept? Okay, so now we're talking about these water molecules, and this water molecule has a partially positive charge where the Mickey Mouse ears are, and a partially negative charge where the Mickey Mouse head is. This is a polar molecule. On this water molecule, there's a partial positive here and a partial negative here. In this water molecule, there's a partial positive here, partial negative here. Because there's a difference in charges right here, there is going to be an attraction. So this water molecule, the Mickey Mouse head part, is going to be attracted to the Mickey Mouse ears of another water molecule. And here too, there's going to be an attraction here. So right here in between the water molecules is what we call a hydrogen bond. Hydrogen bond is right there in between. And that's because these Mickey Mouse ears are hydrogens, okay? And they're causing there to be a positive charge in that part of the molecule. And then there's a negative charge on the other molecule. So these Mickey Mouse ears are attracted to the other molecule. And so that attraction that makes them kind of stick together is called a hydrogen bond. And water molecules do stick together. Okay, this is why you can have a huge cruise ship that weighs a gazillion tons not sink to the bottom of the ocean. It's because it has this huge surface area that's flat, and all the water molecules in the water are sticking together, holding up this huge ship. So that's how that works. Okay, that's it for today. And I hope you have a really good rest of your day, and I will see you next time. Bye-bye.